All right, so chapter 1, we covered a lot of theory and basic math that we'll need for chemistry, but now we're actually going to get into the concepts behind chemistry. We're going to start with the basics. And the first question I have for you is, what is an atom? It's kind of an abstract concept, but does anybody have an idea? Building blocks. That's a great descriptor. So it's a building block. Of all matter. So that's pretty important, right? I once heard it described as the little Lego pieces that are used to build things. That's also another way you can think of it. Another good idea behind atoms, though, is let's say you take a piece of gold foil and you cut it with scissors, and then you get your new piece and you cut it, and you do that over and over and over and over and over and over and over again until you get to the smallest part that you can no longer cut. You're down to an atom, right? So it's the smallest piece that can't be split. Or actually, let me reword this. I'll just say cannot be split into the smaller pieces. This comes with a pretty big exception. Does anybody know what that exception is? I think we mentioned it before on one of the first days. Anybody?
Nuclear fission?
Yeah. So nuclear bombs are the one exception to that. Nuclear bomb, what you're normally splitting is either uranium or plutonium. Most modern atomic bombs are plutonium. This is a picture from the Bikini Atoll tests. These are actually hydrogen bombs. So they're fusion-fission bombs. These are ginormous. If you're interested, reading about the Bikini Atoll is fascinating. Unfortunately, the US government wasn't the most ethical back then, and we displaced a huge number of indigenous people. We nuked their islands, made it radioactive, and then told them they couldn't come back for another 50 years. Even today, people are slowly starting to migrate back to these testing sites, but they're still fairly contaminated, so there's concern about people moving back. So atoms are pretty interesting. They can be thought of as either the smallest building blocks, or you can think of them as a huge energy reserve in the case of plutonium or uranium. One thing that blows my mind, though, was when I was in school, atoms were just described as this theoretical thing, right? But today we can actually observe them. So this is a video produced by IBM where they're actually showing individual atoms. So let's take a look at this. Come on, internet. So every single one of those dots is an atom, and they can actually move them around with lasers. In fact, the Nobel Prize that was announced today in physics was actually about moving matter with lasers. So it's actually closely related to this video. Even more advanced techniques, you can look at entire molecules and see how they're bonded and arranged in a three-dimensional network, which is pretty fascinating. But this was one of the first videos to really show the power of some of these new filming techniques. So it's kind of a clever, interesting video. I think it's fun to watch, but I'm a nerdy like that. All right, moving on. We have to talk a bit about scientific laws and matter, but let's do a bit of review before we go too far. Does anybody remember what a theory is? When we described it in the first week? Is a theory a summary, or is it an explanation of something? It's an explanation, right? So a theory is an explanation supported by data. Where a law, in this case a scientific law, is a summary, not an explanation. And the key thing to remember is that laws often have a formula associated with them. And a lot of scientific laws are kind of no-brainers when we think about them, but when they were first developed, they're pretty cutting edge. So we'll start with the easiest one first. The first one is conservation of matter. Or conservation of mass, I should say. And this is a simple law. Doesn't really explain why it occurs. It just says if you add up two different starting materials or one starting material, the things going into the reaction should equal the mass coming out of the reaction, right? So in this one, we've got 100 grams of mercuric oxide. When we react this, we can get 92.61 grams of mercury plus 7.39 grams of oxygen. So really what this means is that we've got 100 grams going in. And this equals both of these, which are 100 grams of products. Anything we describe going into a chemical reaction is called a reagent. So I'll just write reagent. Anything coming out is referred to as a product of that chemical reaction. So it's a pretty simple concept, right? Any matter you put in or mass you put in, you should also get out. What they didn't know for a long time was that gas does have mass, right? You can actually weigh gases. It's not an easy thing to do, but you can do it. So you do have to account for the mass of any gas that's created. So mass cannot be created or destroyed. All right, so that's a first pretty simple law. And let's take a look at another idea behind this. This next one, I'm going to actually show you a chemical equation. And in this equation, we're reacting methane. So it's one carbon with 4 hydrogens attached to it. We're going to take methane and we're going to react it with oxygen from the air. That's 2 oxygen atoms bonded together. This is what occurs in most furnaces that are fed with natural gas, right? You take natural gas, you react it with oxygen, give it a spark, and does anybody know what the products are when you burn something? Yeah, you get heat, that's one thing, but heat's kind of abstract, right? What are the chemical products? Give you a hint, think about global warming. Why are we trying to limit the amount of fossil fuels that we're burning? CO2, exactly. So CO2, that's one carbon with 2 oxygens attached. The other one's a little bit abstract. What do you think? H2O. Whenever you burn stuff, you actually get water out as well. Normally it's water vapor. When you burn it, you don't actually see water droplets forming because it's too hot, right? It's actually blasted off as steam, essentially. All right, when we look at this, though, things don't look entirely right. We can't create or destroy matter or atoms, right? So when we look at this one, we could say, all right, there's 1 carbon on the reagent side. There's 1 carbon on the product side. That makes sense. We've got 4 hydrogens on the reagent side, but we only have 2 on the other side. So what chemists often do is they say, all right, we're going to plug in a 2 here. That essentially means that when we do this reaction, we actually create 2 water molecules, not just 1, because we have to account for 4 hydrogens going in and 4 hydrogens coming out. All right, so now we've checked carbon and hydrogen. Let's do oxygen. Looks like we've got 2 oxygens on the left. If we think about water over here, we've got 2 water molecules, each of which have 1 oxygen. So that's 2 oxygens from each water molecule, or from both of them combined together, and then 2 from CO2. So that's 4 oxygens on this side over here. So we need to multiply our O2 over there by 2. We're going to practice this a lot more later, but this is called balancing reactions, right? And so when we look at these, you can say, all right, for every 1 molecule of methane, we need 2 molecules of oxygen. And then we get 1 molecule of CO2 out plus 2 molecules of water. And like I said, this is the ratio of reagents. These are also referred to as reaction coefficients. And like I said, you can view this 2 ways. You can basically say total mass in equals total mass out. Or you can think of it as number of atoms in should equal the number of atoms out. It's the same idea, same concept. Does that make sense? All right. Like I said, we'll practice balancing reactions a lot more, so don't panic if you can't do that right now. I just want you to remember mass in should equal mass out, and you can't destroy or create atoms. All right, the next one is a bit more abstract. Let me slide this picture down. And this is called the law of defined proportions. All right, and the law of defined proportions is pretty simple. It says that a compound contains the same elements in the same ratio. And so the example we saw previously was water. If we think about water as a compound, it is shown as H2O, which means that it's always 2 hydrogens for 1 oxygen. So pretty simple idea. If we change it to H2O2 and have a 2-to-2 ratio, then it's hydrogen peroxide. It's no longer water. So we want to be very careful about that. All right. So I'll show you this pictorially as well. So in the first one, what we have is 10 grams of lead reacting with 1.55 grams of sulfur, and we're making a molecule called lead sulfide. I believe in lab this week, you're doing an iron and sulfur lab, right? It's actually pretty similar to this, but instead of lead, you're just reacting iron and sulfur together, and you're going to see what happens. In this example, though, you're making lead sulfide, and there's a couple of things to notice. First thing is we've got 10 grams of lead plus 1.55 grams of sulfur. If we add these 2 together, that should equal the mass of the products we get out, and yeah, we do. So if we look at this one, it looks like a perfect ratio. Of lead to sulfur. And how do we know that? What would happen if we added more lead? We'd probably have unreacted lead left over, right? Which is shown in the bottom example. Or we could have extra sulfur and sulfur would be left over. So when it's a perfect ratio, that means you have no leftovers. If we look at the second example, you can see we added 1.45 grams of sulfur. So if we add extra sulfur, it will not react. It'll just kind of hang out, watch the reaction occur, and then just be there when the reaction's done. Same thing with adding extra lead, right? If we add extra lead, we'll still have lead leftovers. Another way of thinking about this too is instead of a ratio of whole numbers, you can think of it as a percentage, right? So you could say, all right, if you take 1.55 grams of sulfur, divide that by 11.55 grams of lead sulfide, that gives you a percentage of your product that should always be made up of sulfur, right? We're never going to change that. So you can think of it as a ratio or a percentage composition. Does that make sense? Feel free to stop me if I'm not making sense. All right, I'll show you one of my favorite examples. This example involves water. And with this one, we're going to take water. We're going to react it with something called a catalyst. It's basically something that allows the reaction to take place. And we're going to also apply an energy source. And when you do this, you can actually split water apart into hydrogen plus oxygen. And hydrogen in its natural state is a gas. So to show that, we'll often add a G in parentheses afterwards to say this is a gas, it's not a liquid, not a solid. Same thing with oxygen. It's a gas, so we'll indicate that. All right, if we look at this, we've got 2 hydrogens going in, 2 hydrogens going out. That checks out. If we look at it the way it's written now, we have 1 oxygen going in and 2 oxygens going out, so we do need to fix this. However, like I said before, you can add in these multipliers. Say for every 2 molecules water, you'll end up with 2 molecules of hydrogen and 1 molecule of oxygen. So now if we look over here, we've got 4 total hydrogens, 2 in each water, and then we're getting 4 total hydrogens out, 2 from each molecule of hydrogen. Now if we look at oxygen, we've got 2 oxygens, 1 from each water going in, and then we've got 2 oxygens coming out because there's 2 oxygens and 1 oxygen molecule. All right, so this is a big deal right now. Like I said before, we're trying to get away from burning fossil fuels because it emits a lot of carbon dioxide into our atmosphere, and carbon dioxide is a greenhouse gas. This is thought of to be a future alternative because what we can do is we can actually store this hydrogen in these big tanks and use it as an energy source. I went to Iceland a few years ago and got to travel around, and Iceland's pretty unique because they're basically sitting on massive volcanoes. They've got a limitless supply of energy, right? They actually just drill down into the ground and use that heat as an energy source. And because of that, they're able to just take water that's naturally available, split it, and store that hydrogen for free. And they give it out for free in Iceland. The big problem in the rest of the world, though, is we don't have a limitless supply of energy. And in fact, most of the energy we produce on the East Coast comes from burning coal. So that's really just shifting the problem around, not solving the problem. However, we're trying to find better and better ways to do this. So the big one now is trying to use solar energy or geothermal energy as a way of splitting water molecules. It's a pretty interesting field. And when you do this reaction in the lab, you have this big tube of water. This is just regular, plain old water. And then down here, you apply voltage to it, so maybe some sort of energy source. And then these are catalysts as well. And when you let it run for a while, you'll get bubbles coming off of your cathode and anode, meaning both sides. And then you'll collect oxygen on one side and hydrogen on the other. And one thing you might notice with this is the oxygen isn't as full as the hydrogen side. But this makes sense, right? If we think about the law of defined proportions, we said it's composed of twice as much hydrogen as oxygen, right? So this shows us visually that there is a 2-to-1 ratio of hydrogen to oxygen in water. So it is kind of neat that you can experimentally show the makeup of a lot of these compounds. Does that make sense? Bit abstract. A lot of times people are like, yeah, this is pretty self-explanatory, but it was cutting edge when it first came out. All right. So once these two laws were developed, people kind of combined them together into something called atomic theory. And this was done in the early 1800s, so much later. And this was developed by a person named John Dalton in 1803. And the big thing with atomic theory is it's not a law, it's not a big summary that's supported by a math formula or anything like that. Instead, it explains those laws. All right, and there's some key parts to his theory. I'm going to kind of summarize them as best I can. The first one is he said that all matter is composed of atoms. Again, this was kind of a no kidding reality that he came up with, but at the time it wasn't that clear. Oftentimes there was a lot of mysticism involved, and people thought that maybe there were spirits or something special that were helping to compose molecules as well. He was saying, nope, they're just made up of atoms, that's it. All right, number 2 says that all atoms of a given element are alike. However, this comes with a big exception. If you think back to the atomic bomb example that I was showing you earlier, how many of you know about Hanford and the enrichment process that was done in the early part of the war, World War II, that is? So the big thing that they were doing then was not all uranium can be used to make an atomic bomb. In fact, they're dealing with that with other countries like North Korea today. Instead, what they actually have to do is they have to separate out atoms by types of atoms, and those are called isotopes. So it's isotopic enrichment, and that's what we're dealing with a lot of countries today and trying to get them to stop enriching weapons-grade plutonium, for example. Okay, so that's a big caveat. We'll talk about isotopes later. The second thing says, and they are unique from other elements. Specifically, they have different physical properties, right? So maybe they have a different density, maybe they have a different boiling point, different melting point, things like that. All right, like I said though, we'll put the caveat in here that he didn't know about isotopes. Some elements actually behave very differently if they're a different isotope. All right? 3 says that molecules are formed when atoms are combined in a fixed ratio. This essentially explains the law of definite proportions, right? So like we said, water is always going to be 2 hydrogens for every 1 oxygen. And then last but not least, he says that chemical reactions involve the rearrangements of atoms. So like we saw before with water, when you split water, you're basically cutting bonds and rearranging them into new molecules. And then we can also add on to this, which cannot be created or destroyed. One interesting thing he didn't know about was anything regarding nuclear chemistry. So again, there's another exception. Specifically, if you have something that undergoes a nuclear reaction or is radioactive, it will actually change an atom of one type into a new type. We're really not going to cover that in this class though, but I feel like I've got to tell you this, that way I'm not lying to you. Are there any questions with atomic theory? It's a lot of stuff that makes intuitive sense today, but like I said, back then it was pretty amazing. All right, the next person to come along that really made a big leap in chemistry was a person called Dmitry Mendeleev, or Mendeleev, if I'm pronouncing that right. And what he did was he tried to organize elements by their reactivity. Basically, when he was alive, they were discovering more and more and more elements, but they were just a random hodgepodge of elements. He was saying there's got to be some sort of order to this, right? So he was trying to organize them based on their reactivity. The cool thing with this is sometimes he would find a really nice pattern of reactivity where he'd say, oh, every 5th element has the same reactivity, but then there'd be gaps in his table. And he'd say, well, that's weird. We don't have an element with that reactivity. But then they would find that element later on. It was just that they hadn't discovered it yet. So he predicted undiscovered elements. And he liked to call it a periodic trend, right? Because it wasn't that every atom had the same reactivity. In fact, it tended to repeat itself. So I'll show you an example of this. It's a little hard to see here. But let's take lithium, for example. He was able to get a sample of lithium, and what he found was that if you put it into water, it's super duper reactive. It'll start fizzing, produce hydrogen, and you can actually catch that hydrogen on fire. So it's reactive with water. And then as he goes down the periodic table, most of these don't react with water, don't react, don't react, don't react. And then you get to sodium down here. Sodium has almost the same reactivity as lithium, but it's even more reactive. So it reacts the same way, just to a greater extent. And then same thing, you go down, you can find potassium. And it seems to repeat. So you can see the gap between those is about the same. And potassium's even more reactive than sodium. And so he organized this into a big table that we now know of as the periodic table. So if you look over to the periodic table, right, look on the far left-hand side, so column 1, you'll see hydrogen on the top. Kind of ignore that. That hydrogen's there for a variety of reasons. But right below that, you've got lithium, and then you've got sodium, potassium. He didn't know about rubidium, but he predicted that it would be there, and we discovered it later, and then cesium later on. What do you think is going to be the most reactive? Going up or down? Yeah, as you go down, it tends to get more and more reactive. And I wanted to show you this video. I will apologize. There's some crude language in it, but I think it's kind of fun.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
Do you mind flipping the light? Yeah, so one of my funniest lab experiences was one of my friends was in lab cutting potassium. Potassium is actually a metal that's very soft, so you can cut it with a butter knife. So he's in lab cutting it, and potassium is normally stored in an oil, right? Because you don't want it to react with even water in the atmosphere. So humidity is bad for potassium. So he's cutting it, and then it accidentally caught on fire. A metal fire is really hard to put out. So needless to say, I came back into the lab. It smelled like burnt rubber, and then I saw a lab coat that was charred, and then rubber gloves that were melted, and then just a note that said, "Gone to bar." Alkali metals are really, really dangerous to work with. They won't actually let us bring it into the classroom here, which is why I show you the video, but it's fun to see. All right, so if you look at his table, this is what his table looked like. Like I said, he organized things by column, so each column has very similar reactivity, but you can see his table has a large number of gaps in it. Those were all the elements where he predicted that there was something there that we just hadn't discovered yet. And you can see today our periodic table is much, much, much bigger than what he had. Specifically, he got up to, I don't know, he got up to uranium, which is pretty good, but he didn't find a lot of the other really, really large elements. And in fact, if you look at our periodic table in this room, it goes up to 111. We've actually created more elements beyond that. I think it goes up to 118 today, but those are all man-made elements, so you have to use a particle accelerator to make them. And even when you make them, they exist for a fraction of a second and then immediately react or fall apart into other molecules, or atoms, I should say. So it is pretty interesting that he was able to organize all of this. Like I said, today it's all organized by column, and there's a lot more. We'll talk more about this tomorrow, but I did want to give you a brief introduction showing you that reactivities are similar going down a column. Yep?
So the reason the alkali metals explode like that, is it because they're reacting with the oxygen in the water, or?
Not quite. So they're really, really, really strong reducing agents, and we'll talk about what a reducing agent is later on in this term. So what they do is they react with water and create hydrogen gas. Hydrogen gas can explode. Yeah. Yep, so that's where we'll stop today.